Okay, so welcome back, uh, my dear students. Welcome back to the ABCD of Process Dynamics and Control Design. Uh, we have arrived at the fourth day of this course, of the short-term course. Okay, so we have discussed in these 3 days. We are not going to summarize there now. So yesterday we have started with some PID controller problem, PID concept. Okay, so we have started the controller concept yesterday, and today we will continue that concept and extend the issues in the PID controller and how that issues will be covered. We will see. Okay, so okay, so we have uh, the industrial controllers, and as we have discussed in this controller, what is the use of the controller? Basically, uh, controller is used for controlling the some physical parameters. Here, in this case, the composition, or you can say the concentration. As per the measured value and the set point value, this will calculate some error, and according to that error, the controller will send the signal to some valve, and then this valve will act. The valve will open or close it as per their values. Okay, so this is the concept for the basic concept of the automatic controller. And remember always the industrial controller always act in your the feedback path. Okay, so there are different types of controller used in the industry. The basic, the conventional controllers are. So the first one is the proportional controller, second one is the integral controller, third one is the derivative controller. Okay, and then there is one more controller, that is the on-off controller. Okay, so uh, and then there's the hybrid or the combination of controller or three the controller. First one is the PI controller, second is the PD controller, and then the PID controller. Okay, so as we have discussed, the controller will act on the basis of the error. Okay, so we have yesterday we already have discussed this is the suppose controller part. Okay, GC part, the gain of the controller, and this is, let's say, the error signal uh, entering to the controller, and the error, as per the error, the controller signal, the controller will generate some signal, that is the P. Okay, so the P is the output of the controller, E is the input of the controller, right? So basically error is nothing but the whatever the set point is sent to the set point set point is sent to the system, and whatever the measured value. So set point minus measured value is your error, and this error is directly proportional. This error is directly proportional to the error. Okay, so this is the concept of the proportional controller, right? So this output is just directly proportional to this error, and such concept is utilized in designing the control. This the name, that name is proportional controller, right? Now, the when the proportionality constant will removed, then one constant is there, that the constant is known as equality. That constant, equality constant, is known as Kc, and Kc is nothing but the proportionality constant. Okay, proportional gain, you can say this is the proportional gain, right? And those, so thus this equation represent that equation, Pt is equals to Kc into Kc, Pt is equals to Kc into Pt, but some bias value is written here. This bias value represent some steady state value, right? That this value is written here, some steady state value. Why big steady state value? As I told earlier, in some of the case, let's say your operation is running from several times. Okay, and you have disturbed the operation at, let's say, this time. Okay, so then the steady state of this this operation was previous was this one, and at this point we have disturbed the system, and then some transients will come, and then again it will achieve some steady state. Okay, so whatever the steady state was in previous, this steady state was your bias value. Okay, okay, this is not the value, this is not zero. Okay, this value is not zero, it is some value. So we have taken some reference. Okay, so therefore we have taken p bar. So pt equals to p bar plus kc into et represents the proportional equation, proportional control equation. Generally this is in generally the control book you got pt is equals to kc into et. So no harm in writing in this equation also, but as I told you, we have written the actual, the physical equations. The physical realizable equation is like this one p bar. Okay, p bar is nothing but the steady state as we have taken from the previous value. Okay, so so we have p bar, some solve this equation using some mathematical calculation, algebraic equation. So this is kc into et. Okay, so pt minus p bar, when you taking this side, so pt minus p bar is represented by p bar. Okay, p bar is equals to kc into et, right? And when you take the as you know, the Laplace represents the ratio of output and the ratio of input. The ratio of the output and the ratio of input represents the transfer function when we're putting all the initial condition zero in the Laplace transform. So p, now the equation, final equation becomes p s upon es. Okay, is given by simply kc, right? Kc. So this is the case, and this is the proportional constant. This is the equation. This is the transfer function for the proportional controller. Now again we have, I have shown you uh, the basically the controller, the controls is the proportional controller is in the digital implementation. For the digital realization, it is in the digital realization, the p and e are shown in the form of 0 to 100%, right? So as the all the controllers, in the real times, in the today problems or the today available in market are generally the digital. So in the digital specification, that there is a band gap type of system is given, the specification is given, and the number is lying in between 0 to 100%. So in that, in this specification, your valve is open in the term of percentage, right? So suppose 0 to 100% valve, 100% means your valve is open 100%, and 0% means your valve is closed 0%. That is a totally open. Okay, and it is a totally closed. 100% means your valve is totally closed, or 0% means your valve is totally open. Okay, or not closed. So when you supply 10% of the error, okay, so as per there, the control valves will close 10% only, okay, and 90% of the valve is open. Okay, so this is the specification. Such type of calibration is implemented in the digital PP proportional controller. Okay, and this controller, such type of controller has been utilized for the computer software. Okay, now proportional controller. So proportional controller, I have said earlier in yesterday, in the digital implementation, it is always represented in the terms of proportional band. Okay, and the gain into we already also, I think we have covered, gain into bandwidth is always a constant quantity, right? So when you multiply the gain into bandwidth, it will give always a constant value. So here the bandwidth means uh, wait a minute, I'm taking eraser so that you can understood it. So let's say, okay, let's say you have a response of the open and the response of the proportional control like this one. Okay, so this is the off condition. Okay, and this one is the on. This one is the on condition, right? So this term, this value is your basically representing the bandwidth, or you hear the proportional band, right? So you can, as you can realize, this is generally this such type of response will occur in in your proportional controller. Let's say this is your set point. Okay, when you increase the proportional controller, when you increase the proportional controller, such type of response will occur. Okay, such type of response will occur. So this one is the curve. We got the this such type of slope will got in the curve. Okay, or in the response. So this is the proportional band. You can observe such type of response in your practical or in your lab PID simulator. Okay, so now see what is the advantage, what is the disadvantage of proportional controller. So now what happened here, when your proportional band is going to narrow means when you decrease the bandwidth, it means you are decreasing the slope. Okay, sorry, we are increasing the slope. Okay, so when you decreasing decrease the proportional band. Okay, so it means when bandwidth is decreased, it means you are, since the value is since the quantity, the multiplication quantity is constant, it means you have to increase the value gain, and gain is nothing but kc. Okay, and when the kc will increase, this is the kc, this is the proportional band. Okay, so what I mean to say, when you increase the value of kc after a certain limit, what happened here basically, this proportional band is like is looking like this one, looking like this one. So so uh, so uh, so this is basically become, oh, sorry. Okay, so this curve becomes like this one, on or off. Okay, on or off at the time. So such type of controller becomes on-off controller, right? On-off controller, or the bang controller. But that we have discussed. And one student have asked the question in the last. So please repeat the what is the bang controller, right? So it is the concept of bang controller. Okay. Now we have calculated the transfer function. One thing more I want to discuss here. So it means when you increase the gain, okay, the controller becomes on off. However, if you want to use the proportional control in the proportional mode, then it means you have to keep the value kc. You have to choose the value of kc such that it will not act as a on off controller or the on off controller, right? So this is the transfer function for this. Now we have discussed the proportional controller have always offset. Okay, so we have shown from one example. Let's say there is a transfer function of some model of first order model. Let's say this is the tank system. Whatever the tank system is given, it may be the tank system having the transfer function of 1 upon tau s. Now it is said that your supervisor said that please control the level of this tank. Then how will you control? Just to measure the level, okay, using some sensor, level sensor. And you are keeping the feedback gain 1, hs is equals to 1. And you have used the proportional controller for this, and the transfer function for the controller is nothing but kc. And this is the summer comparator, and this from this comparator, this feedback is connected, right? And then this signal going to the controller. And now this is your rs. Okay, this is the rs, this is the set point, and this is the output. Okay, so overall this is become gs. Okay, and this is the feedback is your hs. So the so steady state error that I have not covered in this session. So ESS represent steady state error. Okay, and steady state error depends on the type of the system. So means limited t tends to infinite at t after a very large time. What is the nature of the response that I want to find? So that error is nothing but t tends to infinite. At infinite time, what is the nature of the error? This error is you known as steady state error. Okay, and with the final value theorem, you can say that limit t tends to infinite becomes this limit s tends to zero, s into es, right? S into es, and es is nothing but the rs upon gshs, rs upon gshs, right? 1 plus gshs. So just put the value. Okay, so just put the value and solve this equation. You found out 1 upon 1 plus kc is the value. Okay, so this is the steady state error of the proportional controller when you use with the first order system. So it means this value of kc, this is a 1 upon 1 plus kc. This value 1 upon 1 plus kc is known as the steady state error, and this error is always remains in the proportional controller, and therefore I am saying in the proportional controller there is a steady state error or offset occurs always. As where you increase the value of kc,
सर
obviously the ess will
हेलो।
decrease. हाँ, yeah, hello. हाँ, hello.
हाँ सर, थोड़ा सा टेक्निकल प्रॉब्लम
Hello.
हुआ है, बफर हो रहा है, 1 मिनट।
Okay, okay, no problem, we are wait, I can wait. ठीक है, ठीक है, वेट कर लेते हैं.
यस सर, स्टार्ट कर सकते हैं।
हो गया.
यस सर।
सो कहाँ तक हो गया था मुकेश, कुछ बताओगे? हाँ, कहाँ से रह गया था? ईएसएस हो चुका है स्टेडी स्टेट एरर. हेलो. ओके, नो
स्टेडी स्टेट
प्रॉब्लम.
एरर।
Okay, so a steady state error is nothing due to the some network problem. We just started again. So the concept of ESS is nothing. The steady state error. Steady state error is nothing but the limit whatever the value of error at t tends to infinite or a very large time. So that's such it means suppose you are finding this the response after a certain interval of time, you got such type of response, and this response is this error is nothing but called the steady state error. Okay, so limit t tends to infinite. What is the nature of the error at a very large time or the infinite time? This will say the steady state error. Or when you apply the final value theorem of the Laplace, you got the limit s tends to 0 rs into es. Okay, and what is es? Es is nothing but rs upon 1 plus gshs, right? So just to put the value, limit s tends to s into rs upon 1 plus gs, right? And just calculate whatever we have written previously. So the value of rs is nothing but 1 upon s into s. The value of gc is becomes kc into 1 upon 1 plus I think tau s. Okay, so put the value, and when you put you got 1 upon 1 plus kc. So obviously when you increase the value of kc, the steady state error will decrease. But as you know, as you increase the value of kc, the controller becomes also the on-off controller, bang controller. So this is the problem with the proportional controller. The proportional controller having the steady state error always, that is the offset value. Okay, so for the removing this such type of to avoid such type of problem, we have a different type of controller also, and just therefore we will discuss the integral controller. So integral controller is nothing but again suppose let's say we have the one controller gc. Okay, and this is the error. Okay, and this is the output of the controller, and this controller is again proportional controller is directly proportional to integral of some et dt, right? et dt, right? So when you remove this integral proportional constant, then it you got someone kind of somewhere it is written as in electronics book, generally it is written 1 upon ki. Okay, and in the chemical engineering, in the process industry, we are using this equation as a 1 upon tau I. So you have to know the both the notation, because in the gate exam both the notation will ask. Okay, so tau I is known as integral time or the reset time. Okay, and here the integral constant. This one is Ki, the integral constant. Or such type of control technique is known as a reset or floating control. So floating control and reset controls, these two terms are seldomly used. Okay, so this type of word is not using generally, but its name is reset and floating controller. So this nickname is this one, no problem in this one. Okay, so but you have to remember what is someone in the interview will ask what is the reset controller. So just to say, reset control is nothing but the integral controller. Similarly for the floating controller, right? So the ultimate equation becomes Pt is equals to 1 upon tau integral of ET right? So again, when you write this equation, when you resemble this equation from this written equation, so you again find the p bar is here. So p bar is again say the steady state value, and when we compute the transfer function pt minus p bar, okay, pt minus p bar is equals to 1 upon tau by 0 to t et dt, okay, et dt. So the so this is the p bar. It becomes the equation becomes p bar, and when you find the integral p bar s upon es, and what is the integral of what is the Laplace of the integral? So 1 upon tau y is here, and the Laplace of integral is 1 upon s. So this is the case of the what is the transfer function of the transfer function of this one is like this, okay. This is the transfer function of the proportion integral control, sorry, integral controller. Now if you when you if I say to just to find the value, steady state value or steady state error of the equation, so again we have taken the first order system, and this is the the integral controller, and integral controller is connected with your system dynamics or some system process system, or say I say just control with this one. So now let's say calculate the error. So we have taken the input is the step input. So generally we are taking the step input because the step input disturbance is always taken in some step, okay, not a random. Okay, okay. So we are changing, let's say we are changing some value from, let's say the flow is right now 200 kg per hour, okay. After some time it will change at at this time we have changed the flow 300 kg per hour. So this is generally a step, okay. We are changing the input in the step generally, not always. We have taken the sudden shock also, but generally we are giving such type of input, okay. Therefore we have taken 1 upon s. So when you solve this equation, okay, steady state error again rs upon 1 plus gshs. This one is rs, this is 1, and but this is gs, and hs is hs we have taken in unity feedback. And then you calculate when this value, then got zero error. So what do you mean by zero error? So it means steady state error in the integral controller is zero. So this is the one of the big advantage of the integral controller, right? So integral controller improves the steady state value, but the problem is until unless, since this is the integral, so this is the integral value, so until unless 0 to t, unless until the error will not minimized or zero, it will it will run, okay. So जब तक ये 0 to t टी 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 जब तक उस समय तक चलता रहेगा जब तक कि उसको सिग्नल को एरर को जीरो नहीं करता है, और तब तक ये इंटीग्रेट होते रहेगा लाइक दिस वन. सपोज दिस इज द वैल्यू, तो दिस वन चलता रहेगा उस समय तक चलेगा जब तक कि आपका एरर जीरो नहीं आएगा, ओके. तो therefore the process is the integral control action is very sluggish, okay. This is a very sluggish system, right? So remember the disadvantage of the proportional control is your steady state error. However, the integral control eliminates this steady state error, that offset, but having very sluggish response, okay. So इससे होगा क्या कि बहुत देर के बाद हमारा सिस्टम कंट्रोल होगा. Suppose you are going to control the some temperature of some chocolate industry, right? और आपको चॉकलेट की क्वांटिटी, आपको तुरंत आपको चॉकलेट के टेम्परेचर को टेम्परेचर सपोज 85 डिग्री रखना है, और 85 डिग्री सपोज 90 डिग्री हो गया, 90 डिग्री तक पहुंच गया, तो उसका मतलब है कि उसका क्वालिटी खराब हो जाएगा चॉकलेट का। और 85 डिग्री से 75 डिग्री हो गया तो अच्छे से वो मिक्स नहीं हो पाएगा, चाहे जो भी हो। इस तरीके से नहीं होगा तो क्वालिटी उसकी खराब हो जाएगी, राइट। सो व्हाट वी हैव टू डू, वी हैव टू अचीव 85 डिग्री सेल्सियस एंड सस्टेन्ड and maintain at that temperature only, right? So so for that purpose, such type of controller is not useful again. So what we have to do, we have to search different type of controller, and that controller is your derivative controller. Okay, so before this one, I've just okay, okay. Now, so elimination of offset is usually an important control objective. What we have said earlier, the integral controller used by itself because little control action takes place until the error signal persists for some time. Proportional control action takes immediate. So when you use the PI controller, okay, when you use the PI controller, so PI, when both the combined combination of the proportional integral controller when you use, so what happens? So the speed of the proportional controller is comparatively better than the integral controller, right? It is not very sluggish. However, it has some problem of offset. Uh, 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 whereas the integral controller, we have the problem of sluggishness, right? But sluggishness, but this has it improves the steady state error problem. Okay, so when you combine both, it means it will speed up and it will the integral controller will the improve the steady state error. Both of them, both of the combination of both are improves overall the system. Okay, there what is the equation for this mathematical? So, but just we have written PT is equals to P bar. This is the bias value, and we have given Kc into Et. Okay, this is the proportional controller, and Kc into 1 upon tau. This is the integral controller. So this is the combination of the PI proportional plus integral control, right? Now we found the transfer function of this one. So PS upon ES, okay, and this is for the Kc into Et, okay, and this is for the Kc of 1 upon tau s. So when you solve this equation, such type of response will got transfer function will got. Okay, okay. Now, what is the disadvantage of integral controller? As I told you, this is the oscillatory response. Oscillatory response means until unless your response will go on, it will always gives error. Okay, so this is a problem with the integral controller, right? So therefore it is sluggish, right? So when you supply the sinusoidal input, okay, sinusoidal input as input, it means we are not giving some a step or something else. So when you apply this type of input, then it means just to try to find the output of the response. So for the first order, for the PT, so what will happen when you supply this one as an error? So your equation is like this one: PT P dash is equals to nothing but the Kc into Et, or Et is your sine omega t 1 upon tau integral 0 to t integration of sine omega t dt. So this one is the equation, right? Now when you solve this one minus Kc of tau I and when integrate this one, we got 1 upon omega cos omega t. And just to solve this just solve this equation, okay, we got the equation like this is the amplitude, and as we have discussed one problem 1 upon s plus 1, and I have told earlier, this is a question asked in the gate examination also. When you supply sine omega t, okay, and you have asked what is the response of the system. So I told at that time, when you supplying some sine omega t or sinusoidal signal, your output must be sinusoidal, Only there is only change in your magnitude and as well as in the phase. Okay, so here also the input is sine omega t. So we have applied with this system kc upon 1 plus tau is. Here the kc upon 1 plus tau is here. Okay, and then we applied then such type of, this is the amplitude and this one is the phase change we got. Okay, so this is the plus. Okay, this is the plus sign with the tan inverse in this one. So therefore, I am saying the controller. Therefore, it is sorry. Okay, this is a minus sign. Okay, so this is a minus sign is here when you solve this equation. So it means it is lagging by some 10. This value, this value is lagging with this value, and therefore the characteristic are similar to the lag compensator, or the lag compensator is nothing but the low pass filter. Okay, so low pass filter. The low pass filter, you know what is the low pass filter? As you, I think you have covered in the network theory, what is the meaning of low pass filter, high pass filter, and what is the characteristic of all pass filter, right? So I'm not going to cover that part, but you know what the, suppose 1 upon s plus 1 is here. So if you want in the Laplace transform or in the transfer function, if anyone asks to you, so what is the what is the low, what is the transfer function is a low pass or high pass or the all pass. So just to try to put this s is nothing but the frequency j omega. Okay, complex frequency j omega plus 1. So it is, you know, omega, when you, it is as a low pass or high pass. So check omega equal to 0. Omega equal to 0, it means the low signal you are sending. So when you're sending omega equal to 0, it means you got non-value g, non-zero value. And when you got the non-zero value, it means the signal is the low signal, the low frequency signal is passing. Now put the value, the very high value, that is infinite. When you put the infinite, it means is the response you got 0. Okay, so when you got the response 0, it means nothing, no high signal or no high frequency is going to pass. So it means such types is similar to the low pass filter. Okay, I'm giving one more example. Let's say s upon s plus 1 is there. So now, if you want to solve this equation, so take the common s, so it becomes 1 upon s, right? So this is the equation when you solve, and when this s is putting, when s equals to j omega, and put this value omega equal to 0. So again it becomes 1 in 1 upon infinity, and this will give 0. Okay, so the low signal is not passing here. However, when you put the omega n, it becomes 0, and 1 upon 1 becomes a non-zero value. So it means this the high signal is here passing. So this is the case of the low pass filter. You can differentiate, or you can find out which type of system is low pass or high pass. One more case is here. Suppose let's say s minus 1 upon s plus 1 is there, and someone is asked find out the nature of the filter. So you can find out using the value of putting the j omega, or try to find out. It is the all pass filter, right? Now I come to the very interesting topic that is usually not covered in your class, or usually not given in some Indian book. It is generally given in some most reputed book like Kafner and Siborg. Okay, so that is your reset wind up. Okay, so there is one more problem in your, you know, integral controller. As I said, integral controller have some sustained oscillation. Okay, so either this oscillation will goes uh, until unless the error is not minimized, or error is not very going to settle down. Okay, so integral term will act at that period, for that period. Okay, so in integral disadvantage, I action is phenomenon known as reset wind up. Reset wind up is generally occurred in only in the integral controller. Okay, so due to the integral controller, it will be maybe in the PI controller, and it may be in the PID controller. Okay, so since due to the only the integral controller, not due to the proportional and derivative controller, it is only for the integral controller. Okay, So integral controller cause the controller output change as long as it is equal to 0. As long as it is not equal to 0, the control action will act. Okay. So now when a sustained error occurs, listen very carefully. Yeah, this such type of question is asked. Okay, in the interview when you sit in the IES examination or somewhere. So if you are the man of control system, then such type of question will ask in your interview. Okay, so question is, uh, so if the sustained oscillation occurs, okay, when the sustained oscillation occurs, okay, the integral term becomes quite large because it will never ending. ओके, ये तो कभी एंड होगा ही नहीं, चलता रहेगा चलता रहेगा चलता रहेगा चलता रहेगा चलता रहेगा, सस्टेंड ऑसिलेशन. ओके. सो कंट्रोलर आउटपुट इवेंचुअली सैचुरेट्स. तो ये क्या करता है, कंट्रोलर का जो आउटपुट है, आउटपुट ऑफ द कंट्रोलर सैचुरेट कर जाता है वहां पर. क्या कर जाता है, वो कुछ रेस्पॉन्स नहीं करता, रिस्पॉन्ड नहीं करता वहां पर. So such type of saturation, such type of saturation is integral control or integral wind up or integral wind up. Okay. So this is a problem in the integral controller. तो करना क्या वहां पे, जब भी इंटीग्रल कंट्रोल आपको करना क्या है कि सस्टेन ऑसिलेशन नहीं आने देना है सिस्टम में. सस्टेन ऑसिलेशन कैसे नहीं आएगा, तो आपको यू हैव टू चेंज सम इनपुट ऑलवेज. ओके. सो let's say indicated area is this one is given. Okay, so reset wind up occurs when a PI or PID controller encounters a sustained error. So sustained error जब भी आएगा, as you know, then such type of problems will occur. और sustained error कब आएगा, large set point change when you provide some large set point change. तो लार्ज सेट पॉइंट का मतलब आपने सडनली 100 से मान लो 1000 kg पर आर दे दिया आपने, तो ये बहुत ही लार्ज आपका फ्लो रेट है. और इस फ्लो रेट के चलते क्या उसको सेटल्ड होने में बहुत टाइम लगेगा. तो आपको क्या करना है, यू हैव टू चेंज योर इनपुट इन द स्टेप, इन द वेरी स्मॉल स्टेप साइज, इन द वेरी स्मॉल स्टेप साइज, सो द एरर मिनिमम. ओके. सो such type of problem may be avoided with the help of such arrangement. Okay. Now first one more interesting controller is here. Okay, the derivative controller. So derivative controller, as as the integral controller is known as reset or the floating controller. However, the derivative controller is known as anticipatory controller because it anticipates. How it anticipates, we will discuss here. So rate action, how it is, why it is called the rate action. The answer I will give you in some moment. Okay, it is called pre-act action. Pre-act action, basically the derivative, the idea of the derivative control is used for the idea of the derivative control used for the anticipation. Anticipation means some type of prediction, and pre-act action. Okay, so prediction means we have taking some rate. Okay, so if you know the rate, let's say I'm giving we are illustrating this concept with one example. Let's say, so first of all, you understand what the anticipatory what the meaning of anticipation. You know, prediction. The function of decontrol action is to anticipate the future. If you are able to predict the future behavior, then it can be called as the anticipate. Okay, so how it is defined? It is defined you from the change or rate of change. Okay, if you are able to determine the rate of change, how? See, suppose that a reactor temperature increases by 10 degrees Celsius in a short period of time, say 3 minutes. Suppose that a reactor temperature increases by 10 degrees Celsius in a very short time of say 3 minutes. 3 मिनट में कितना टेम्परेचर बढ़ जा रहा है, 10 मिनट 10 डिग्री सेल्सियस. 10 डिग्री 3 मिनट में 10 डिग्री सेल्सियस बढ़ जा रहा है. दिस क्लियरली is more rapid increase in temperature 10 degree Celsius rise in 30 minutes. तो इसका मतलब हमें ये पता चल गया कि 3 मिनट में सर 10 डिग्री हो रहा है, तो अगले 6 मिनट में 30 मिनट में 50 मिनट में कितना होगा, यू कैन एंटिसिपेट द वैल्यू. ओके, सो इफ यू नो द रेट d/dt, okay, if you know how the y will change with this time, then you are able to predict the future also. So this is the case. Okay, so now what is the live problem? Live problem is your covid covid-19. Okay, as you all listen, covid-19. So we are already passing from unprecedented the in the covid-19 we have many more literatures are modeled this system, developed a model based on their data. Okay, so one model that you can find out in the Google SIERD model. SIERD model. Okay, so when you say SIERD model, so this is from the recovery from the death. Okay, uh, I exactly not remember just the suspectability. Okay, and evolution, and I don't know the I don't remember exact the definition of this one. However, this model is basically based on some relation between the death, recovery, okay, uh, uh, evolution, and sustainability. So 5 to 6 equation is given, and based on this data and model or the differential equation. Okay, my one of the BTech students and combined with MTech students has done this project under me this year, and he has yeah, they predicted the flattened curve will come after the September. Okay, but due to the unavailability and due to the not accuracy of data, we can't say this model is very right. Okay, whatever the data is available on the net, we can model such a model, and we have reported that result in some the journal. So see, so it means prediction means you can draw the predictive model with the help of such type of arrangement. Okay, so if the reactor were under manual control, the experienced plant operator would anticipate the consequence and quickly take the appropriate correction action, reduce temperature. तो अगर उसको पता है कि इस रेट से चेंज हो रहा है टेम्परेचर, तो जो ऑपरेटर है दे कैन take they become very conscious about that, and they can take the quick action against the same, right? So what the concept? The concept is PT is equals to, this again, this the suppose let's say this is the controller, and the controller is nothing but here it is defined the term of tau d. Okay, tau uh, tau d, or somewhere it is written kd. So in the electronics books generally it is written kd, and in the process book it is generally written the tau d. Okay, so reads like this one, and the KD electronics engineer, electrical engineers will can study like this one. And since I am the instrumentation engineer, so I will read both the notation. Okay, so somehow. Uh, so KD is there, tau D. So this means P is directly proportional to derivative of d by dt of error. Okay. So this is the concept. So on the basis of this concept, this is written. Again, remove the proportionality constant, and we can arrange, we can accommodate this tau d value here, or this pt minus p bar becomes okay p bar, and we can find out the transfer function also. So the transfer function of this tau d becomes the transfer d by dt, Laplace of d by dt is s into es. So p bar into e is nothing but t tau ds. Okay, so this is the Laplace of the problem. The transfer function of this one is tau ds. Okay, so now tau d is known as derivative time. Okay, derivative time where the tau I was known as integral time or reset time. Okay, so control output is equal to the nominal value p bar as long as the error is it's well known, no problem. And deviation is action is never you. This is a very important line. So D control action is never used alone. Okay, it is always during the conjunction of proportional control. So why it is not used? So there are two reasons why. First reason, first reason. See here. Uh, let's say if you give the if you give what is the d by dt of ut, what is the differentiation of ut, this is a step taken generally taken input as an input as an input the step input. Okay, so when you use the step input in this, this is the error. Okay, so when you When you use such type of input, then you got delta t, and delta t is nothing but impulse. Impulse means there is certain shock in the system. So as you apply the error like this one, you got the, after the control action, just gives a very sudden shock to the system. And therefore, to avoid such type of sudden shock, if this sudden shock may harm your system or may affect the system very poorly, and therefore we are avoiding this type of the input. And therefore the derivative controller is never used, because you can't change your input, because you are changing the signal, the step, from such type of step change. Calculate the steady state error. As you know, the limit extends to 0 s into rs. Now since the s is not, we are not using rs as equals to ut. So what is using, we are using 1 upon s squared ramp function. Or due to the ramp function, when you differentiate the ramp function, when you differentiate the ramp, so there is no problem in this one. But when you differentiate this one, then you got the impulse. Therefore, we are not using the impulse step signal in the case of derivative. So therefore, derivative controller is not used, because you can't change the using of this one. Okay, so 1 upon s square, then when you calculate this one, then you got the steady state error is infinite. A steady state error is infinite. However, since this is the d by dt, this d by dt, so the error, the function is depend on the derivative function. Then therefore this network is very, this arrangement is very fast. Okay, so this is not very sluggish. So what is the meaning? Integral controller so sluggish, but the error is zero. However, the error is infinite, but the response is too fast, and we are able to predict the future also. Okay, so combining all this property of the controller pi, and we have studied p controller, pi controller, derivative controller. Now the time to cover the pd controller. Okay, so in the PD controller, as you know, the transfer function becomes Kc, because what is the transfer function of this one? Kc upon tau d into Kc into E, okay, and d by dt of E function. So this is your transfer. This is the equation for this one. When you solve this equation, so we have taken the Kc as a common. So Kc is multiplied with this all the function, basically no problem in this one. So when you solve this equation, we can write like this one. Okay, the gain. So this Kc and 1 upon 1 per tau ds. Okay, so this is the transfer function for the PD controller. Okay, the derivative control action tends to improve the dynamic response that I told. It is a very fast. It gives a very fast response, but there but there is a very high error. Okay, of the control variable. By decreasing the process settling time decrease, it decreases the settling time. Okay, but it will, it will produce a very high error. Now, since this is the 1 upon tau ds, and since that the term, it is defined with the help of derivative terms. So if there is any noise in the system, if there is any noise in the system, the process measurement is noisy. That is, if it contains high frequency, random fluctuation, then the derivative of the measured variable will change widely. As we have said, as we have seen, when there is any change, like a step or something, it will act. ये फौरन वहां पर एक्ट करेगा, और फौरन उसके जल्दी से एक्ट करने से क्या होता है कि ये सिस्टम को बहुत हार्म करता है वाइडली. ओके, द वैल्यू चेंज वाइडली, and derivative action amplify that noise unless the measurement is filtered. So what we have to do for the avoiding such type of, we can't avoid the equation. Okay, this is the property of the controller. Okay, this is the property of that. This is the beauty of this controller. So we can't change this one, but we can ignore the noise. We can ignore the noise. So how it can be noise? So how can we ignore this noise? We can ignore this noise with the help of some filter techniques. Okay, we can ignore this noise with the help of some filter techniques. So derivative control is seldom used for the flow control because the flow control loops are respond quickly and flow measurement tends to be noisy. Okay, so it is generally used such type of system in the process industry. Unfortunately, the ideal PD control algorithm, but they have sold physically unrealizable. It is not physically realizable. Okay, physically it is a very important line. Physically unrealizable system. Okay, it cannot be implemented exactly using their analog or digital components. Okay, so we can't be able to design the exactly we can design like this one. So what is the correct method? Because the it is you can't ignore number you can ignore the noise at very much extent. Okay, you can't ignore can't make the noise zero. You can't make the noise zero. So what is the best method? Just we have used the equation in some filter term. Okay, so it is 1 upon tau ds, 1 plus tau ds, but it is written like this tau ds upon alpha tau ds plus 1. Okay, when you solve this one, you got the equation like same like this one. So Kc, it is the conventional, it is the method, it is the equation by which the PD controller is designed. Okay, so that equation is Kc 1 plus tau ds upon alpha tau ds. So the value of alpha is fixed from 0.05 to zero point 0.2, and typical value is given here 0.1, right? So this is the value. So I think to understand why such type of equation is written, this equation is written only for to avoid the noise. Okay, but I have already told the 100% noise can't be ignored, can't be removed. So this equation is known as derivative mode filter. Okay, it reduces the sensitivity of the control calculation to high frequency noise in the measurement. Okay, so there is no problem. So remember, we will discuss once again such type of this during the tuning. Right now, PD controller is capable of improving transient state. Okay, PD controller is capable of improving transient state, but that I have told earlier. Now come to the input like sinusoidal. So when input is your sinusoidal, then when you find the output of this controller, then you got the change in the phase is changed in the plus sign with plus sign. So it means it is when since this is the plus sign, so it represents the leading type of nature. Okay, and therefore it is known as lead component discuss s upon 1 plus s plus 1 up 1 plus s, and the nature was the in nature was the high pass. So you can imagine, you can again implement such algorithms or such techniques to calculate either which type of which form is this one. So using this you can compute this is the high pass filter. Okay, now when proportional control action is used in the reverse mode, the error is reduced from infinity to some finite value. That is not for you. Okay, no problem. So now come to the different design part. Okay. Now first, I will cover you. Basically, this is a proportional type. This is basically parallel form of PID controller. Okay. So for the parallel form of PID controller, we have taken the KC. We have taken from the sorry. This is the KC when it is multiplied with the KC. Okay, 1 plus 1 upon tau y. This is the integral term, and this is the the derivative term. And when all these are finally added, then multiplied with the kc, and this is your transfer function p bar s, okay, into es. Okay, so this is the given. Okay, so how it is written mathematically? One, it means cases which we have taken common, or this is the et when you es is multiplied with es is multiplied here, es is multiplied here. So we have taken like this. Okay, so this is the transfer function for the PID control, parallel PID controller. Again, now see the series form. Okay, uh, it's a parallel form, no problem. It's a parallel form. Sorry, I forget to uh, design this one is so this one is I forget to give the the series form block diagram, no problem. So the transfer function for that portion, that series form of the ID controller is represented like this. And generally, this equation is used in the real-time manufacturing of the PID controller. Okay, so why it is written in the form of some filter form. Okay, this is S, this is I, and when you want to given this one, so it is the represent the proportional. Okay, so Kc is when you 1/1 per tau is is the PI controller, and this is the derivative controller, right? So this is the PID controller of the series arrangement, right? And this derivative controller is written in the form of filter form so that we can avoid you know the noise. Okay. Now there is one problem in the derivative controller, that is the derivative kick. Okay, the derivative again I am telling you, this type of terminology is generally not taught in the class. Okay, so derivative kick, what is the derivative kick? Just listen. This is the one of the disadvantage of the derivative controller. Okay, so what I told in the previous two slides. Okay, okay, wait for 2 minutes, huh? Then I will. Okay, wait for 2 minutes. Anis, my voice is audible? Okay. So, can we start? Okay. Okay. So, you are live? Okay. Is the slide is visible? Okay. Yes, it is visible. Okay, now. Okay, so we are discussing about the range, typical range, basically. Okay. So, हाँ मैं बोल रहा था कि आपको ऐसा नहीं है कि कुछ भी आपको रेंज ले लेना है. नॉट एडवाइज टू टेक एनी वैल्यू ड्यूरिंग द सिमुलेशन of the PID controller, right? So if the value is fixed, okay, so you can't be during the simulation. You try to solve, you try to tune the value, whatever the value of Kc, from 0.1 to 100. Okay, if this value, if your response is you're not getting the satisfactory from this range, then try to change the controller type. Okay, and then combine this one, okay, with PI or something else, ओके. सो इन द प्रोपोर्शनल कंट्रोलर को दो तरीके से मैंने आपको डिजाइन करके बताया. फर्स्ट है आपका एनालॉग टाइप एंड सेकंड इज डिजिटल टाइप. So both are the using in the designing for the industrial controller. Nowadays, digital controller is used. So the proportional band is defined. That's 100% by KC, and that percentage is given like this one. Okay. तो इंटीग्रल मोड में 0.02 सेट आपको 20 मिनट टाउ आई की वैल्यू लेना है. 1 upon टाउ आई यू कैन डिवाइड एंड यू गॉट द करस्पॉन्डिंग वैल्यू. ओके. uh, as an electrical engineer or as the electronics engineer, the value is k. The value of constant ki is fixed like this one. Okay. Similarly, for the derivative controller, this data is given, and you can simulate your problem like this one. Is it okay? So now see the response, controller response. What happened with the different type of controller when you use? So in the first controller, this is the typical response with feedback control. Okay. So when there is a no control, that is a simply feedback control, feedback system is used. Such type of response you got. Okay, such type of response you will got. But when you apply the proportional controller, then the second type of this response you will got, right? This response you will got. Okay. Now, when you're talking about the wait a minute. Okay. When you talk about your PI controller, then the PI controller. So this is the PI controller, right? This is the PI response. Okay. So again, you can say due to the integral controller, the error is drastically changed. Okay. The error is sorry. This is the, I think, PD controller, and then is this the PI controller. Okay. Okay, and this is the PID controller. So you can say, sorry, this is the PID controller. Okay, one is missing, I think. One is missed. Okay, no problem. No problem. So this is the response for the PI controller. This is not the, here we have not the PD controller, right? No problem. So PI controller improves the steady state, you can say. However, as we introduce the derivative controller, it makes the it speed up the system transient. It improves the transient very fast, and then such type of response will got. So it is a no control, it is the proportional control, it is the PI control, and then the PID control. Okay. Now see, this is the proportional control action we have used. Okay, in the only the proportional control action is used here. And now we are going to increase the value of Kc. Here the Kc was zero. When Kc was zero means you are not using any type of proportional control or any type of control, right? As you apply the proportional control and you increases the value of Kc, okay, then such type of response you will got. Okay. Now what happened with the tau I? This is the integral controller. Okay. And when you use the integral controller, as you can see, the value of it is the PI controller basically. Okay, this one is the proportional plus integral controller, and we are varying only here the integral term, that is the tau I, and you can see the response is changing. First, this is one is the or more oscillatory, then it reduces the oscillation, and then it more reduces the oscillation. Okay, it means tau as you increase the value of tau, the oscillation will reduces. Okay. Similarly, in the case here, it is your Kc value where you are increasing the value, you are decreasing the value of Kc, and you got such type of response, right? So this is the PID type. As the you can see the tau d. Why we have not used then the PD? Okay. So as you we know the proportional derivative controller is generally not used in the control system. Okay. So this is a practical problem. PID control is used here. Okay. So it is the effect of derivative time is shown here. So during the tuning time, you can understand why such type of arrangement has been done. Okay. Now it's a time to realize the PID controller or some type of any type of controller using some electronic circuit or the electrical circuit. Okay. So one method is given here using the op amp. So using the op amp, you can design. So you know the how the op amp will work. As I told in the one of the slide, at that time I said it is one of the important slide because I will again use this slide. So you know the virtual mode concept has been used in the uh, op amp. So this is zero, this voltage is zero. So automatically this virtual mode, due to the virtual mode concept, this is voltage is zero, and whatever the current is flowing from this side is totally going to the this side because the resistance of the this side is very high, that is the infinite. Okay. So for the ideal op amp, so as you know this the voltage is here vi, so you can write vi minus 0 upon z1s is equals to you know whatever the i1 as is equals to i2. Okay. So okay, so 0 minus vi minus 0 upon z1 is equals to 0 minus v naught upon z2, and from v naught is equals to you can find the value z2 s upon z1. Again this is the transfer function. Okay. So now you understood what is the meaning of transfer function, the relation of the output and the relation of input in the Laplace transform, and you have put it all the initial condition 0. Okay. So these are the some concept used here, and with the help of this concept, okay, with the help of this concept you can determine the different, you can realize the different type of controller. Let's say this is r1 and r2 are used here. This is the r1 and this one is r2. So your transfer function becomes minus r2 by r1, and it is nothing but a constant value. So you can say this is the gain type of controller, or simply this is one is the you know this one is the case proportional controller type. When you use RC type, RC means always remember RC means integral and CR means differential. But whenever this after the C the R will use, then this is the differentiator. Okay. A differentiator is the lead compensator. Okay. A lead compensator is a low pass filter, right? So you have to remember this one. Or RC, sorry, this is the high pass filter. Okay. And this is the low pass filter, right? So as you can remember such these things. So when you use C here, and then this is R, then you can realize the transfer function. Okay, like this one. When PI controller, so for the this is the P, and this is for the RI. So RC controller this becomes, and this is the differential, and this is the proportional. Then it will like look like this. And where the PID controller for the proposed in derivative terms, and this is the proportional integral term, and all the terms will become gives like this one, and this is the PID controller. You can design like this. Okay, so you can see here this is the derivative term. This one is 1 upon s into something. 1 upon tau is this one. This one the tau ds, and this one is the constant kc. Okay, so this is the kc. This is the tau d, and this is one is the 1 upon tau I. That is you can say change. You can take the value of tau I. Okay, so as per your convenience, you can solve and try to find out the you can design the PID controller. Okay, so this is the lag compensation and lead compensator. Okay, now we are arrived at the tuning time. Okay, so have you seen such type of transistor radio in your home? खासकर हमने बिहार वाले तो हमने देखा ही है, हमारे बिहार वाले घर में ऐसा इस तरह का हम लोग रेडियो रखते थे गाँव में, है ना? तो ये गाँव में बड़ा चलता था हमारे। तो और पहले तो बड़ा 90 के दशक में ये बहुत ही उस समय प्रचलित था, है ना? तो उस समय हम लोग क्या करते थे, इसको हम लोग पहले एक एम, आज की डेट में तो एफएम चलता है. सो द टुडे जनरेशन आई मे बी not aware of such type of system, but in the those who are aware of the 90s के जमाने में जो लोग जिए हैं, उस समय 90 से पहले के लोगों ने इसको देखा है. ठीक है. तो हम लोग उस समय क्या करते थे कि दिस इज द एम और दिस इज द एफएम. ओके. सो एएम और एफएम में हम लोग क्या करते थे कि हम लोग ट्यूनिंग करते थे, है ना, चैनल को सेट करते थे. और एफएम में एज यू नो द वॉइस क्वालिटी इज वेरी क्लियर इन द एफएम, है ना. एंड हाउएवर द वॉइस क्वालिटी इज नॉट वेरी क्लियर इन द एएम. सो हम लोग एक चैनल आता था विविध भारती. तो विविध भारती के समय हम लोग क्या करते थे कि हम लोग ट्यून करते थे, है ना. और ट्यून करते समय क्या होता था कि दूसरा चैनल भी साथ में कभी कभी पकड़ता था, है ना. तो उस ट्यून करने का क्या मतलब हुआ कि हम लोग इसके अंदर एक इंडक्टर टाइप, ये इस टाइप का बना होता क्वाइल, सॉरी, इंडक्टिव नॉट इंडक्टिव, सॉरी, द कैपेसिटिव टाइप. एंड वी आर चेंजिंग द capacitance or based on this. Okay. Or then the tuning is occurred. Okay. So it's a topic of the electronics, however. But what's the meaning of tuning? We just want to inform you. So from that value, you can tune that channel and listen the music, whatever. Okay. So meaning of tuning means choosing the optimized value. Okay. Tuning means you are choosing the optimized value in the given, value. So whatever the values is given, as per your desire, you choose some point where the where you want to set the value. Okay. So the verb tuning in radio context means adjusting the radio receiver to receive the desired radio signal, carrier frequency that particular radio station uses. Okay. So you want to set your frequency at which the radio station will run. Okay. So now, what motivates the control engineers to tune industrial controllers? So again, I am telling you, this topic, this such type of topic is not going to cover in your class generally, but more recently, from 2014 or 13, it is found that the electronics engineer or the electrical in the electrical engineering and the electronics engineering, such type of problem is now asked. Okay, for the tuning of the PID control in the gate examination. Okay, so what is the meaning? What the motivation for the tuning? So as you know, it is the plant and this is the PID controller. And for the PID controller, there is a value of KP. Sometimes it is called KC. Okay, or sometimes it is called KP. No problem in that one. So tau ds and tau is here. So PID is going to control the parameters, physical parameters of that plant. Suppose temperature, whatever the level, depends on the plant desire. Okay. So the setting of the fine tuning of KP, tau is and tau ds. As you have seen in the table, you have to choose one value at which the PID control performs very good. So what there is a range of this one, there is a range of this one, there is a range of this one. So it becomes the problem of optimization. Okay, this is the problem of optimization. Optimization means you have to choose a one of value where all one of the set of values, okay, set of the values of kp tau I tau d, where the the controller performs or gives your optimum set process parameters, or the optimum response. So what do you mean by optimum response? You can understood by the we have already studied in the second order system about the settling time, rise time, about the delay time. So at that time, we have said we have to minimize as we want to achieve the set point as soon as possible without any delay, without any overshoot, without any error. Okay. So these are the performance parameters. Okay. So we have to optimize the performance parameters with the help of this PID controllers, and we have to choose the PID controllers. We have to choose the value of these parameters uh, in the optimum way. Okay, so right, see, these PID controller may be arranged in the parallel form here, and maybe the response like is looking like this one of this controller, or this is the interactive type of PID controller. You can arrange the PID controller in this form also, no problem with this one. And you can design the proposed PID controller in this form also. So this is the interactive form. However, this is the non-interactive form. Okay. This is the parallel algorithm we have discussed all earlier. Okay. And this one is see this table. Okay. This will decide the tuning of the PID controller. See, this is the parameters. Okay, this is the performance parameters of the any control system. Okay, so students may advise to listen it very carefully, and if you have any query to just to ask from me. Okay, from this topic, because this topic is very very important for your gate exam purpose, or maybe for your research point of views, or when you doing some project based on the control system. Okay, so what happened? Uh, s- your rise time basically will decrease when you increase the value of KP. So it is when you increase the value of KP, it will decrease. The overshoot will increase. Settling time will change. There is small change in settling time. It means there is no effect on the settling times. However, the steady state error will decrease. The stability quality will degrade. Okay. Similarly, this is the KI. As I told, the proportional controller may be written in the form of KC, or in the electronics engineer it is written is like KP. However, the electronics or electrical engineer write the integral term in the form of integral constant that K and KD. Okay, so there's no problem. So KI is nothing but 1 upon tau I. So you are increasing the KI, it means you are decreasing the tau I. Okay, so you can understand like this also. So as we increase the KI, the rise time decreases, the overshoot increases, settling time increases, the steady state error eliminated, okay, and the stability degrade, however. Similarly, the KD, it is totally based on the simulation, okay. So I will show you from one simulation so that you can understand it very easily. So the KD, the minor change is occurred in the rise time, overshoot. This one is the this criteria is like this. Okay. Now after 10 minutes. 10 minutes. So what is the conclusion? Conclusion is you have to choose the value of P, the value of I, and the value of D. Okay. We have to choose the value of these parameters such that okay, you got the performance parameter optimum. So all these value are interdependent. Okay, or depend on the process also. Okay. So what is the goal? Our goal is to compute our what is the goal? Our goal is to choose the compute optimum value, that is the value of KP, KI, and KD for the satisfactory response. Am I right? What is the meaning of satisfactory response? What is the meaning of when I'm saying satisfactory report response or the optimum response? What this means? So optimum doesn't means maxima. Optimum doesn't means minima. It means whatever the आप सपोज आपके पास 10 लोगों की टीम है. ओके, और 10 लोगों की टीम में कहें कि आप हमको एक ऑप्टिमम वैल्यू दो, तो आप उसमें से क्या करोगे कि सबको तेज को लाके नहीं देना है. सबका परफॉर्मेंस एक जैसा नहीं है, लेकिन सबको मिला के आपको बेस्ट परफॉर्मेंस लेना है. उसमें हो सकता है कि कोई दूसरे सब्जेक्ट में अच्छा हो, कोई दूसरे सब्जेक्ट में अच्छा हो, कोई दूसरे में अच्छा है. So just like that, we have just minimize somewhere, okay. We compromise somewhere, okay, so that we can do like that, okay. So we are finding some optimum value, okay. So minimum overshoot is we want from the system, we want just from the system the minimum overshoot, okay, no overshoot from the system. Settling time as soon as possible, we will we want to arrive, we want to arrive here at as soon as possible in a minimum time, okay. The rise time is very minimum we want from the system. The rise time should be very minimum. Minimum steady state error we want from the system again. The error should be as minimum as possible, or, or ideally zero, the zero error. Next value is 1 by 4 QAD. It is one of the most important terminology used in the chemical process plant. Okay, QAD. What is this? The quarter amplitude delay. We will see in the next slide what the meaning of this one. So we want also. So for the designing of any controller or such this you have to maintain. Okay. So this you have to maintain the overshoot also. It has maintain this response also. Including this, you have to maintain the QAD ratio. Now satisfactory set point tracking with high disturbance rejection. So we have to maintain, or you have to track the set point. You have to track the set point with the rejection of the disturbance. Okay. So you have to set point, you have to track the set point, but at the same time, you have to reject the disturbance, whatever the getting from the environment. Okay. The environment means, let's say, this is the the, let's say, the term flow is going inside this one, okay. You are controlling the flow from this one. So this will act as a disturbance, okay. This flow is act as a disturbance, okay. So we have to uh, you have to act as a disturbance, okay. So now this is a single performance criteria. These are the performance criteria known as single performance criteria, okay. So wait for a moment. Some my call is coming. Hello, hello. हाँ जी. कौन? सर मैं लेक्चर ले रहा हूँ, मैं आपको कॉल करता हूँ सर आज, है ना. आज कॉल करता हूँ अभी आपको. सॉरी, सॉरी फॉर द इंटरप्शन, सॉरी फॉर द डिले. ओके, ओके, ओके. So this the minimum. This all this criteria are known as the single performance criteria, right? Now come to the decay ratio. So this is the basically decay ratio. What is the decay ratio? Quarter amplitude delay ratio and quality quarter. This is the 1 by 4. Okay, amplitude decay ratio. This is known as quarter amplitude decay ratio. Quad ratio इसको कहते हैं हम लोग. और व्हाट इज द मीनिंग ऑफ क्वाड रेशियो? देखो, यहाँ पर जो हमारा मैक्सिमम एम्पलीट्यूड है, मैक्सिमम एम्पलीट्यूड का मतलब ये क्या है? हमारा फर्स्ट ओवरशूट है, ओके. और ये क्या है? हमारा हमारा सेकेंड ओवरशूट है, ओके. So this is the overshoot. This one is the overshoot. This is the first overshoot. This is the second overshoot, and the ratio of a this amplitude and this amplitude is same to 1 by 4. So what is the benefit? Why we are defining? So ये वाला और इसका रेशियो, ए और बी का रेशियो हमारा क्या कहलाता है? क्यूएडी कहलाता है, डीके रेशियो कहलाता है. सो क्या इसका फायदा है? देखो, एक तो पहले ग्रीन सिग्नल क्या है? ग्रीन सिग्नल इज सेट पॉइंट. व्हाट इज द ब्लू लाइन? ब्लू लाइन सेज द प्रोसेस वेरिएबल, ठीक है. तो ये प्रोसेस वेरिएबल है. अब व्हाट इज द रेशियो? दिस रेशियो विल डिफाइन द क्यूएडी. नो प्रॉब्लम इन दिस वन. सो व्हाट इज द सिग्निफिकेंस ऑफ दिस वन? अगर ये हमारा 1 by 4 है, इसका मतलब इसका और इसका रेशियो अगर 1 by 4 है, इसका मतलब ये हुआ कि ये जल्दी से सेटल हो जाएगा. ये क्या हो जाएगा? ये सेटल्ड आपका जल्दी से हो जाएगा, यानी 4 टाउ, सेटलिंग टाइम 4 टाउ. 4 टाउ के बाद हमारा जो सेटल टाइम है, आपका सेटलिंग जो है, दैट विल अचीव्ड, ओके. therefore we have defined like this one, okay. The ratio of the a and b should be 1 by 4. So it is a poor choice. However, it is a poor choice of process stability. मैं आपको पहले बोला ये आपका बहुत अच्छा choice तो नहीं है, but this is one of the choice. Okay, the idea behind the QA is to eliminate any error between the set point and the process value very fast. So we can achieve the settling as far as possible. Okay, so nothing in this. Although the quad tuning objective provides very fast rejection of disturbance, it creates three problems. Okay, so these are the problems. Just to read. Okay, just to read these problems in the PPT. I will provide you. Now another satisfactory response. These are the satisfactory response that mentioned here is known as a single performance criteria. This depends on the single performance. Okay. However, the another performance criteria that is given here is the multiple. Okay, or you can say the time integral performance criteria, and this one is the multiple. Okay, so when you minimize IAE means error, integral absolute error. Okay, so when you going to minimize integral absolute error, so basically, as you are going to minimize all the parameters. Okay, that is the rise time, settling time, overshoot, and whatever the written here, the QAD. If you minimize this one, all these parameters are involved in one line and one word. You can say that is the IAE, ITA, IC, ITC. If any of the parameters as per the your desired problem, as per the problems, you can optimize this. If you are able to optimize this equation, then based on that you got the satisfactory response. Now it is a function. Okay, it is a function. That function is nothing but the set point minus the measured value. Okay, and when you integrate this one of the function, then this is known as a functional. Okay, one term is used in the control system, optimum control, that is optimal control. This is the functional. Okay, functional is the function of function is known as basically uh, function of function. Okay, the audience is generally from the Bihar, so I assume that the mathematics of our state is very strong. So so you know the function, already know the function, what is the function, what is the function of function. So the function of function is generally known as the functional. So this is the functional equation. Okay. So if you are able to uh, optimize or minimize these things, then you are able to get the satisfactory response. Okay. So first idea is your integral absolute error. Second is the integral time absolute error. A third is the ISC, that is the integral square error, and generally this is used for the optimization. Okay, this equation is generally used for the optimization. And third is the ITSC. Okay, third is the ITSC. This is integral time square error. Okay, integral time square error. So our target is to minimize this one, and I'm not going to detail of this one because if we go into the detail of this, then the problem becomes the optimization problem, and this is the again the next a separate separate subject, or that is the optimal control. Okay, so I'm not going into this topic. Okay, so now time integral performance criteria. So the question is at which time which type of problem, which type of criteria you have to choose. Okay, so this is given here, the time integral performance criteria. Now, Amitesh, hello,
Yes,
Amitesh,
sir.
we
Yes,
have
sir.
time now.
Yes, sir.
We can continue
Yes, sir. We can continue.
up to 6 o'clock.
Yes, sir.
Okay, no problem. So I want to cover today at least the PID controller concept all. Tomorrow we will discuss the tuning of the PID controller, Jaden, and next Cohen. Okay. So today we want to finish this one. There, is it okay?
Yes, sir.
Okay. So when such type of this type of आप to choose आपको कब चूज करना है ये सारा, ये आपको उस समय आपको अभी पता चल जाएगा कि आईआई कब चूज करें, किस तरह के प्रॉब्लम में आईटीए यूज करें, किस तरह के प्रॉब्लम में आईएसी यूज करना है, किस तरह के प्रॉब्लम में आईटीएसई यूज करना है. वी हैव टू सी हियर. So for that, now select the type of controller, okay, and the value of its adjusted parameter in such a way as to minimize the IAC, IAE or ITA of the system response. हमें करना यही है. Ultimately, we have to minimize this value. Okay. Now the selection of any one of the criteria depends on the characteristic of the system we want to control. So ये इस कौन सा select, what is the selection criteria of choosing this one? That depends on the characteristic of the system. What are the characteristic of the system? See here. If you want to strongly suppress the large error, if your error is very large, okay, if your system respond in the feedback control without any controller, it will give a very large error. Then IAC is better. Okay, then IA. So use IAC in comparison to IA because the error are squared. In this case, integral square error, you are going to square the error and then contribute more value of the integral. Okay, okay, because integral minimizes your error. Okay, integral minimize as we have seen in the integral controller. Okay, so okay, so integral minimizes the error as integral will act until unless the error will not minimized. Okay, so if the error is squared, then its contribution becomes more, and therefore the ISC is advisable at that place for the suppression of a small error. If the error is small, then you use IAE. Okay, no problem. To suppress error that persists for long time, if your error persists for a long, very long time, then you use ITA type criteria. Okay, that will tune the controller better because the presence of large T. Okay, so T will, that is the ramp function, and to the ramp function it amplifies the effect of even small error in the value of integrals. Okay, so this is the some criteria. By if you follow this one, then you are able to apply this type of uh, which type of performance criteria you choose, okay, or select. So this is the control loop, general control loop in the process control industries, uh, uh, when you use when you have to control the flow parameters, then proportional type of controller is advisable. Okay, however integral controllers usually used, but derivative controllers are never used. In the case of level control, again, proportional is always used with a combination of integral, but derivative controllers are used rarely. But these are the two parameters that, however, the temperature, if you use the temperature is for the temperature, uh, you have to control the parameters very quickly. This such type of parameters. Okay, so uh, for that purpose uh, for that purpose uh, for that purpose, the proportional control always used, integral control usually used, and derivative control also used. Okay, so analytical, in the case you can see from this table, analytical and for the pressure. Okay, so what we have concluded here, what is the meaning of tuning, we have understand. What is the meaning of good control, we have understand. The good control means satisfying our criteria, okay, optimal criteria. And the optimal criteria, what is this one? Single performance criteria or your integral time, whatever that is one. So good control parameter optimization problems that we have tuning problems. In many of the, there is a no control model process and the criteria of good control is value defined. So you can understand our one quarter ratio and the overshoot. Okay, so this is the criteria given. Okay, so I think what next? We will tomorrow we will try to learn the trial and error method, process reaction curve techniques for the tuning, Ziegler-Nicholas tuning method, and the Cohen-Kuhn method. And then the time will allow. Then we will discuss the frequency analysis. Okay. And one more topic, the data driven. One student have asked on the day one, what is the data? How the data driven model are formed using the neural network. But I promised I will cover the regression. But if the time will allow, then tomorrow we will cover this topic for. Okay. So okay, thank you very much for the parent for me. So just to take, I'm just now taking some problems, some query from your side. Hello, हाँ कैसा? हेलो सर यार ना तू घर पे चल, तू कर, तो मैं आ रहा हूँ.
रूम नंबर कितना है सर अपना?
B9.
B9 ओके सर.
ठीक है, B9 में उसको तुम करो, मैं आता हूँ, है ना?
ओके सर.
है ना, मैं 10-15 मिनट लगे बस, है ना, मैं आता हूँ मैं, ठीक है. आई एम कमिंग इन 15 मिनट्स. ओके. सो Amitesh.
Yes sir, query has been shared on your email.
Okay. Okay. So okay, I'm just checking. Take the feedback of the student also, so that the student get benefited. Okay, उनके जो
Yes
कमियां
sir,
हैं अपन उसको ले
feedback
लो.
कर लेंगे सर.
हाँ, और नहीं, तुमको डे वन से लेना था, क्योंकि अगर उनको कोई कमी होगा तो उसको उस तरीके से बताया जाएगा. कोई मे भी कुछ बच्चों को समझ में ना आया ना, तो उनसे
Okay
हम
sir,
लोग कर
I will
लेते हैं.
circulate a feedback form right now. So
राइट
if
नाउ,
they
हाँ,
have
आज
any
कर लो,
issue.
क्योंकि कल, हाँ बिल्कुल, और उसको
Okay.
शेयर कर लो, ठीक है. नाउ आई
Okay.
एम टेकिंग वन क्वेश्चन, हाउ टू डिसेबल अ पीआई कंट्रोलर फॉर स्पेसिफिक टाइम पीरियड बाय यूजिंग सम इफ एल्स कंडीशन. यू कैन डू, यू कैन डू. देखो इसमें क्या करना है, इसमें कुछ भी नहीं करना. पीआई कंट्रोलर को आपको कुछ देर के लिए बंद करना है, चालू करना है. वो हमारा कंट्रोलर उस समय आप स्विच लगा दो वहां पर, है ना, वो स्विच लगा के उतने टाइम के लिए आप उसको कर दो. तो सिमुलेशन में ये हमारे पास फैसिलिटी भी होती है. यू कैन डू लाइक दिस वन. तुम ऐसे भी कर सकते हो कि किस टाइम, कुछ देर के लिए कितने टाइम के लिए पीआई लगाना है, कितने पीआईडी लगाना है, कितने पी लगाना है. यू कैन डू लाइक दिस ऑल्सो. ओके. सो इसमें आपको प्रॉब्लम नहीं है. आप इसको सिमुलेट, अब तुम लोग सिमुलेशन करके एक बार देखो मैटलैब पे. कल मैं तुमको एक प्रॉब्लम मैटलैब से सिमुलेट करके दिखाऊंगा, जिससे तुम लोग को शायद थोड़ा बहुत क्लियर हो जाए, है ना. प्लीज शेयर द कंट्रोलर पीडीएफ टुडे ओनली. आज ही कर देंगे बेटा. What is the meant by sluggish response? Sluggish response means slow response. Sluggish means slow, very very slow. Okay. What difference between set point and output? Set point और output का मतलब है, सेट पॉइंट मीन्स डिजायर्ड वैल्यू. आउटपुट, पूरा महाभारत खत्म हो गया और अब कह रहा है द्रौपदी कहाँ है. तो सेट पॉइंट का मतलब है बेटा रेफरेंस वैल्यू, डिजायर्ड वैल्यू. और आउटपुट का मतलब है मेजर्ड वैल्यू. ओके, ठीक है, मेजर्ड वैल्यू. व्हाट यू आर गेट द प्रोसेस वैल्यू, प्रोसेस में क्या आ रहा है, आउटपुट क्या आ रहा है, और तुम क्या चाहते हो सिस्टम से. ठीक है. सर कुड यू प्लीज टेल अस वंस अगेन द प्रोपोर्शनल पर डेरिवेटिव कंट्रोल इज प्रैक्टिकली नॉट पॉसिबल. Okay, so tomorrow we will illustrate with the one example. Okay, so I will cover it. Okay, I am writing this problem. Okay, so why PID PD, तो वो डेरिवेटिव कंट्रोलर में किक होता है. सिंपली बात है, वो सडन चेंज को नहीं सह पाता है. देयरफॉर हम इसको इंटीग्रल कंट्रोलर के साथ यूज करते हैं, जिससे हमारा वो क्या हो जाए, उसको कंपनसेट कर ले. ठीक है. फिर भी मैं ट्राई करूंगा कल आपको एग्जांपल्स बताने की. प्लीज रिपीट सर, व्हाट इज द आईएससी एरर इन कंट्रोलर. आईएससी कंट्रोलर मीन्स इंटीग्रल स्क्वायर एरर. तो जैसे हमारा जो एरर आ रहा था, जैसे हमने सपोज करो एक स्टेडी स्टेट पे हमारा सेट पॉइंट है 10 और हमारा 12 पे जाकर सेट हो गया, या कुछ हमारा ऑसिलेशन आते जा रहा आते जा रहा है कुछ इस तरीके का. तो उस तरीके का हम ले रहे हैं आईएससी, है ना, उसको आईएससी एरर कहते हैं. इंटीग्रल स्क्वायर एरर हम लोग जब लेंगे तो क्या होगा, एरर कुछ भी हो सकता है, लेकिन उसको लेने का तरीका क्या है, वो हम लोग डिपेंड करता है डिफरेंट टाइप्स ऑफ क्राइटेरिया, डिफरेंट टाइप्स ऑफ मेथड है, जिसमें आईएई है, आईएससी है, आईटीएई है. तो एक क्राइटेरिया आईएससी, उसमें से हम लोग इसको कर सकते हैं. ठीक है. लॉट ऑफ प्रॉब्लम इन प्रोपोर्शनल इंटीग्रल कंट्रोलर. लॉट ऑफ प्रॉब्लम मींस नॉट यू अंडरस्टैंड, और प्रोपोर्शनल कंट्रोलर में प्रॉब्लम है. किसमें प्रॉब्लम है, ये इंटीग्रल प्रोपोर्शनल इंटीग्रल कंट्रोलर इज कोई प्रॉब्लम. चलो तुम लोग दोबारा देखना पीपीटी, फिर उसके बाद अगर नहीं समझ में आए तो जस्ट आज गिव द फीडबैक टू द योर फैकल्टी, सो दैट आई कैन modify our PPT accordingly. Okay, और जो समझ में नहीं आया आप PPT में उसमें फीडबैक में सब कुछ लिखिए जो जो समझ में नहीं आया. Okay,
यस
we
सर,
will
अभी सर्कुलेट कर देंगे फीडबैक.
जिससे हम आपको क्योंकि जितना पढ़े उतना समझ में आना चाहिए. टारगेट इज दिस वन है ना. ज्यादा पढ़ना इम्पोर्टेंट नहीं है बट वट एवर यू हैव स्टडीड you understand that clearly. Okay, so can this STC helpful for the future career development? Obviously yes. If you are going to make your career in the control system or in the process dynamics, this course is very helpful. I am teaching this course to the MTech students also, and also those who are pursuing, those who are doing to his research in the PhD. I am also teaching the same subject as coursework. Okay, so this course is very very important for that purpose. I already have been past my research work in in the paper industry, and this that in paper industry is basically totally based on the control part. Okay, so that's why I'm taking all the example of the process industry, that is all the equipment that is used in there. Okay, nothing else about the industrial controller as well as PI controller. uh, just I'm sharing the PPT. If you have any problem, then again I will cover it. Okay. But however, I'm we will going to cover the tuning of the PID control tomorrow. So I hope it may be more clear, it will become more clear. Okay, what is the derivative controller? Again, I have told the d by dt of error. D by dt of error equals to the whatever the output of the controller. The output of the controller is basically d by dt. Okay, so this is the derivative controller, right? So okay, so you have already told D controller can't work alone. I have not cleared about it, sir. अगेन आई एम सेइंग डी कंट्रोलर. आप बस एक बात याद रखो, इनपुट स्टेप जब ज्यादा होगा, इनपुट स्टेप जब अप्लाई करोगे डी कंट्रोलर में, तो डी कंट्रोलर का डी बाई डी टी होगा आउटपुट. और डी बाई डी टी का मतलब है ई. अगर आपका स्टेप होगा तो अगेन इम्पल्स आएगा, और इम्पल्स जब आएगा तो सडन शॉक होगा, और जब सडन शॉक होगा तो आपका सिस्टम खराब हो जाएगा. सिंपल सी बात है. तो इसलिए हम लोग डेरिवेटिव कंट्रोलर यूज नहीं करते हैं. ठीक है, क्योंकि डेरिवेटिव कंट्रोलर जब भी आएगा तो डेरिवेटिव किक लेकर आएगा फॉर द स्टेप चेंज, और हम लोग इनपुट हमारा जनरली हमारा स्टेप इनपुट के फॉर्म में होता है. ओके, so therefore we are not using the derivative controller alone. Okay, sir, as we know that the steady state error in derivative controller is infinite and integral controller zero, then what is the use of derivative controller? डेरिवेटिव कंट्रोलर सिस्टम को बहुत ही फास्ट बनाता है, जबकि इंटीग्रल कंट्रोलर का एरर तो जीरो होता है बट रिस्पांस बहुत स्लो होता है. डेरिवेटिव कंट्रोलर का रिस्पांस बहुत फास्ट होता है बट उसका इनफाइनाइट का मतलब कुछ भी नहीं है, और जीरो का मतलब भी कुछ नहीं है. ठीक है, जीरो कभी नहीं होता प्रैक्टिकल प्रॉब्लम में. आइडियली हमने लिया है फर्स्ट ऑर्डर सिस्टम, तो इसलिए जीरो है. ये मिनिमम को हम लेस वैल्यू का है, और यहाँ पर वैल्यू हाई वैल्यू का है. तो इनफाइनाइट कुछ नहीं होता मैथमेटिकली. हाई इनफाइनाइट इज नॉट डिफाइंड. ओके, so in practical problem, infinite is not problem. That's a very high value. So डेरिवेटिव कंट्रोलर में एरर बहुत हाई होता है, उसको हम लोग मिनिमाइज कर सकते हैं. मैंने बताया पीआईडी के सेटिंग से. यही तो हमें करना है, यही तो हमारा एम है कि कुछ ऐसा वैल्यू चूज करे पीआईडी का, केपी टाउ टाउडी का, जिस तरीके से हमारा पीआईडी कंट्रोलर बहुत ही अच्छा परफॉर्म करे. और उसके मैंने क्राइटेरिया आपको बताया. ओके, सो व्हाई डोंट वी यूज इंटीग्रल कंट्रोलर एवरीवेयर सिंस एरर इज जीरो. मैंने बताया स्लगिश सिस्टम है. अगर सपोज करो तुमको चॉकलेट इंडस्ट्री में 85 डिग्री तुमको रखना है, तो 85 डिग्री तुमने रख दिया, लेकिन वो आ रहा है 1 घंटे के बाद, और आधे घंटे के अंदर तुम्हारा सामान खराब हो जाना है, तो तुम्हारे तो प्रॉब्लम हो गया है ना. तो इंटीग्रल कंट्रोलर इसलिए हम वहां पर यूज नहीं करते हैं जनरली. साथ में इंटीग्रल हम लोग पीआईडी कंट्रोलर हम लोग यूज करना है. क्या यूज करना है? पीआईडी कंट्रोलर. तो पीआईडी कंट्रोल यूज करना है फॉर द पीआईडी कंट्रोल. कुछ इस तरीके से यूज करना है कि केपी टाउ बाई टाउ डी की वैल्यू इस तरीके से फिट करें कि आपका रिस्पांस बहुत फास्ट भी हो जाए, एरर भी कम हो जाए, एक साथ राइज टाइम, सेटलिंग टाइम, ओवरशूट सब कुछ खत्म कर दे. सेटलिंग टाइम बिल्कुल कम हो, राइज टाइम बिल्कुल कम हो, ओवरशूट बिल्कुल जीरो हो जाए. समझ रहे हो? इसका मतलब है कि आईएससी इंटीग्रल स्क्वायर एरर कम हो जाए. समझ रहे हो? अल्टीमेटली these are the things. Okay, so I have covered all the query of all the students. One or two query we will try to cover tomorrow. Okay. So can this STC helpful for the already done? So all the query I have addressed. So I handing over the session to the Amitesh or Anis. Please go ahead, Amitesh.
Thank you very much, sir, for the session. I
Mm.
would like to request you that if possible, then shall we extend the session for half an hour tomorrow,
No problem, no
so that
problem. We
we can,
can
yes, so that we can cover all the topics.
we can cover, Hana, we can cover, but problem is the one problem, small problem. After 5 o'clock or 6 o'clock, my phone is continuously ringing. Will ring. So maybe
Okay, sir,
it
we can
will
start early now, if possible.
tomorrow is Saturday, no? So we
Yes, sir.
can start. We can start, no problem. Okay.
Okay,
So
sir.
we can start at
Thank you.
3:30. Yeah, we can start
Yes,
at
sir,
3:30
3:30.
also. Okay, so
Okay,
that
thank you, sir.
okay, okay, okay. Thank you very much, Anis and Amitesh, for your such a nice organizing your STC. Thank you very much.
Thank you, sir.